Yes, doctor.
Okay, so we were saying that we can apply now between A and C or between B and C. Okay, so because you have this for the same acceleration over the whole path. Okay, but I advise you to relate A and C because A is given in the يعني they are it's given in the question. Okay, for B, if you did a calculation error, it will affect your result. So if we do the relation between A and C, we can write that VC square minus VA square is equal to minus 2G times delta Y. Delta Y is Y of C minus Y of A. Okay? So here, if we apply this relation, what will be the only unknown? The only unknown will be VC because I know VA. So I will replace VC square minus 75 square is equal to minus 20 times y of c is 0 because I am at the ground level. So times 0 minus y of a is 40. So minus 40, okay? Then the only unknown in this equation is VC, so I get VC. Now, if you didn't pay attention to use the relation that is independent of time, you can find in another way velocity at c, but you need to do it in two steps. First, you say at c, what do we have? So second method, okay? You say that at point c, y of c is equal to 0, okay? So if I use the equation of y is equal to minus 5t square because it's half 80 square. So it's minus 5t square plus v0, which is 75, plus v0 yt plus y0, which is 40. Okay? So you can say for y equal to 0, if I put y equal to 0, I can get tc. Okay? So if I apply this relation for point c, yc, which is 0, is equal to minus 5 tc square plus 75 tc plus 40. This is a second degree equation. If you solve it in the calculator, you get two relations, two solutions, one negative, one positive. So of course you will take the positive solution. So we select the positive solution. Okay, and then once I find the time, in order to calculate the velocity at c, I can simply say that v at c is equal to minus gt, which is minus 10 tc, plus v0, which is 75. Okay, so here this is another method to find velocity at c, but as you can see, if you use the right relation, you can reduce the time of solution because you will do it in one step if you use the relation independent of time, but you will need two steps if you want to include time. Okay, any question for this problem? Okay. Another problem, we have a metallic particle is traveling downwards through a fluid that extends from plate A and plate B under the influence of a magnetic field. If the particle is released from rest at s equal to 100 millimeter and at an acceleration of 4s, where s is in meters, determine the velocity when it will reach plate B and the time needed to travel from C to B. So first, I have a function of s and I want to find velocity. So I can directly think about the relation that is independent of time because I want to relate a, v, and s. So I have that a ds is equal to v dv. Okay. if I replace A by its value, I get 4S ds equals to V dV. And now I can integrate for both sides. So the integration of the first side will give me 2S squared. Okay, and here I am integrating between what and what? Between S0 and S. What is S0? They told me that initially it was at point C. Okay, so S0 is 100. So here I will put S0 equal to 100. And from the other side, I have VdV, integral of VdV. I have V squared over 2 between V and V0 and V. Okay, so this is between V0. And what is V0 here? They said that it's starting from rest. So V0 is 0. So between 0 and V. Okay. Now if I replace, I will get 2S squared minus 2S0 squared. So minus 2 times 100 squared. Now please pay attention for something. They gave you A in meter per second square and S of C in millimeters. So please pay attention to convert. So I will not use 100, I will use 0.1 because I need to convert to meter. So minus 2 times 0.1 square, okay, equals to, from the other side, I have V square over 2 minus 0 because V0 is 0. So here you got V as a function of S. Then you can find the velocity when you reach B, because when you reach B, what is SB? So SB is 0.2. SB here is 0.2. Okay. So to find velocity when you reach B, all you have to do, you replace in this equation, you can get therefore VB. Okay. We will continue the second part of the problem next time. Any question on this?
No, doctor, thank you.
No, doctor, thank you.
Okay, bye.
Thank you, doctor.
Welcome.